Hello everyone and welcome back to the sessions on quantitative methods for CFA level 1. Now in the series of lectures on time value of money, right from the beginning we have been talking about compounding. We have learned a lot about compounding of interest, and again in this session we are going to continue with the discussion on compounding, but we are going to go a little deeper and particularly target the concept of continuous compounding. So what we have already learnt about compounding, let us quickly recap the same first of all. So under the heading concept of compounding, we would say to find out future value, the following factors are required. Number one, the rate of interest that is resembled as R or I. Time in years can be mentioned as T or sometimes even N. Basis of compounding is also needed, whether the compounding is annual, quarterly, monthly, whatever be the basis of compounding. So if we go with the annual compounding, we find one thing, that if interest rate is given to you, you can find the future value factor. So if the interest rate is 12% per annum and time horizon is 1 year, whether you borrow or invest $1 at the beginning of the year with 12% per annum interest, by end of the year $1 will become $1.12. You know it very well, right? So the future value factor will be 1.12. If the rate of interest is 15% per annum and the time horizon is 1 year, the future value factor will become 1.15. Let us move ahead and continue further. What if there is half yearly compounding involved, and suppose the rate of interest is 12% per annum and the time horizon is 1 year? You know how you have to do it. You will first take 12% per annum with half yearly compounding, means you divide 1 year time horizon into 2 half years. So if 12% is for the year, half of 12%, that is 6%, will be for half year. That is why what we do is we take 0.12 divided by 2. So the factor for one period becomes 1 plus 0.12 divided by 2, that is 1.06. But there will be 2 periods within 1 year because it is half yearly compounding. As a result, you will have to consider the compounding twice. So the frequency of compounding will be 2 times within a year. So when you make this calculation, that is 1.06 raised to 2. Whatever you get, that you consider as the future value factor for 1 year, because the time horizon is 1 year. So that would become 1.1236. We have learned all this in the earlier classes. This is just a recap for you. Let us see what will happen if it is a quarterly compounding. If 12% per annum is the rate of interest and time horizon is 1 year, you know this time what you are going to do, you are going to break up this 12% per annum into 4 parts. You are able to break it into 4 parts only because the compounding base is given as quarterly. So 1 year can be divided into 4 quarters. So when you take 1 year period, it is 4 quarters, and the rate effectively for each quarter will be 12% divided by 4, that will be 3%. 3% on absolute basis will be 0.03. So it will be 1 plus 0.03 as the factor for each quarter, and because there are 4 quarters in a year, you take raised to 4. So it will be 1.03 raised to 4, that becomes the future value factor. So $1 becomes 1.12550,881, something like that. What if the compounding is continuous compounding? So if it is 12% per annum and the applicable period is just 6 months, we have learned one thing in the earlier class, it will be e raised to r into t. So r is the rate of interest which is based on continuous compounding, and t is the time in years, that will be 6 by 12. As a result, 6 by 12, that is 0.5 into 0.12 will give you 0.06. Now what you need to do, when you pick your financial calculator, you should know how to determine the value of e raised to 0.06. So before you start writing any of this, first pick your financial calculator and do as I say. You take 0.06 on the screen first, and then 1, 2, 3, 4, 5, 6. Sixth row in your calculator keypad, sixth row, first switch is ln, and on top of ln you find e raised to x. X value is already there on the screen. You want to find e raised to x because it is the second function. You press the second key and then press ln. So it is not ln that is getting activated, it is e raised to x that is getting activated. That gives you the final result of 1.06184. 1.06184. So just imagine what is happening. The more the frequency of compounding within a period, the greater will be the future value factor. You know it very well. That means the intensity of compounding goes to the maximum when the continuous compounding comes into picture. So continuous compounding can be considered as the extreme limit of compounding. Nothing can be beyond that. That means $1 will become 1.06184 in 6 months time with 12% per annum continuously compounded. Now nothing or no form of compounding can make the future value factor after 6 months anything beyond 1.06184. That is the extreme limit. So I want you people to please take note of this whole thing. Let us move ahead and continue writing further. Now we are going deeper into the discussion of continuous compounding. So under the heading continuous compounding, please write the mathematical limit of shortening the compounding period is known as continuous compounding. Let us take an example, and let me remind you, this is in continuation of the series of examples that you have been solving earlier. So 28 examples were done till the previous class. So example number 29. If 1000 is deposited at 10% per annum continuously compounded for 5 years, what is the future value? So you know how to compute future value when it is a case of continuous compounding. So it will be f equals to 1000 into e raised to 0.1 into 5. See, e raised to rt. R is 0.1, t is 5 years. Now what you do? It will be 1000 into e raised to 0.5. So how to compute e raised to 0.5? I have already explained to you. Pick your calculator, take 0.5 as input, and once you take 0.5 as input, press second and then ln to arrive at the future value factor, which comes to 1.6487, and when you apply that and multiply to 1000, in fact on your calculator when you directly multiply this factor to 1000, you get the final result as 1648.72, what I have displayed over here on screen. So quickly write up this whole thing and then I take you ahead. Let us move ahead, and now we talk about logarithms. So understanding what is logarithm, this is very, very important. Now at your school level you would have learned logarithms. If I give you a simplest example of logarithm, how to determine a log value, as you have learnt it at your school level, but you should know one thing very clearly, that we have two different forms of logarithm. One which we call as common logarithm or basic logarithm, where the base of the log is 10. And another form of logarithm that we need to apply for financial calculations primarily, that is natural logarithm, which has the base of e. E is the exponent value, which is a constant in mathematics, and it has a definite value 2.71828. Now we are going to understand what exactly is a logarithm, what is the role of log, and how do you apply natural logarithm for financial calculations, particularly in the context of time value of money. So let us crack it one by one. What is the basic difference between the common logarithm and natural logarithm? Common logarithm takes the base of 10 and natural logarithm will take the base of e. So when we say log of a number to the base 10, it is the basic or common logarithm. Log of a certain number with the base of e is natural logarithm. Now when you find the term mathematically used as log, L-O-G, the log indicates generally a common logarithm, whereas the symbol used for natural logarithm is ln. Ln also stands for log normal. So log normal or natural logarithm, its symbol is ln. So ln of something indicates natural log of something, and log of something is indicative of the basic log or common log of that number. Now, if I focus on the basic log first, which takes the base as 10. So meaning of logarithm, I would say with an example, suppose we take square of 10. So 10 square will give you 100. So if you find log of 100 to the base of 10, the result will be the power, which is 2, because 10 square was 100, log 100 will become 2. 10 raised to 3 becomes 1000. So if you take log of 1000, it will be 3. So you understand one thing very well, that log of any number is basically the power. So the base raised to that power will give you that original number. So let me give you this whole thing with examples and with proper defined mathematical terms. A logarithm is the inverse operation of exponentiation. It answers the question, to what power must a certain base be raised to produce a given number? So log of a number is the power to which the base is to be raised to get the number. Now, this line is very, very important. If you want to find out how many times you need to multiply 10 to get 100, you use log 100. So basically, when you take log 100, the result will be 2. Log of 100, the result will be 2, because 10 square is 100. Now please observe, I would say, if 10 square equals to 100, then log of 100 to the base 10 will be equal to 2. Now this is something that you need to understand with proper interpretation. In context of this line, log of a number means log of 100 is the power that is 2, to which the base is to be raised. The base is 10. If 10 is to be raised, so 10 square will give you 100. It will give you the number as 100. So 10 square is 100. So once again, log of a number, that is log of 100, is the power that is 2, to which the base is to be raised. The base is to be raised. The base is 10. It is to be raised by 2 to get the number, that is 100. Let us move ahead and now write the heading as understanding natural logarithm. Now, once you have understood what exactly is the meaning of common logarithm, how to apply that, how to interpret that, same lines you have to apply natural logarithm. Now, just understand one thing. In the previous example, we have taken 10 square, which gave you 100. So 10 square. So 10 was the base and power was 2. Under natural logarithm, e will be the base. So throughout continuous compounding, what are we actually applying? If you can recollect, it is always the present value multiplied by e raised to rt. So it is e raised to something. So when you have to use natural logarithm, the base being e, it will give you the value of the power. So if e raised to 2 is giving you a certain value, then natural log of that number will give you the power which is 2. So you can check, turn on your calculator and input 2, and we want e raised to 2. So what we do is we take second and ln to arrive at the value of e raised to 2. What I am getting is 7.3891. So if I take natural log of 7.3891, what will I get? I will get the power that is 2. So I press now the ln of this number. Ln of this number will be exactly 2. So whatever I have discussed with you, let us just write it down systematically. Under the heading understanding natural logarithm, please write, the natural logarithm is a specific type of logarithm where the base is the mathematical constant, that is e. The constant e is approximately equal to 2.71828. The natural logarithm is denoted as ln of a certain number. So it is ln of x in this case. So if I take ln of e square, I am obviously going to get the value as 2. Why? Because if you are taking ln of e, means you are taking log of e, and when you get log of e with the base of e, the power is basically 2. So log of e square, the result will be 2, because this log is not the common log, this is the natural log. So when you take ln of e square, the result will be 2. I have just shown you that on the calculator. So the next line that you need to write is, because e square is the number we get when we raise e to the power of 2. So if e square is 7.3891, then ln of 7.3891 will give you exactly 2. Let us move ahead and continue further. Write the heading interrelation between e raised to x and ln. So you know, if it is e raised to x, it is going to give you the future value factor, because when you multiply e raised to x to any present value, the present value will get transformed to the future value. So e raised to x itself is the future value factor. Now in time value of money, this x value is the product of r and t. We know it very well. So e raised to x, when you take the natural log of that, that is ln of e raised to x, you know what you are going to get? Ln of e raised to x will return back to the power that is x. So ln of e raised to x is going to give you x. We have seen one thing, if ln of e square is giving you 2, ln of e raised to x will give you x. So e raised to x basically is e raised to rt. So x will be product of r into t. So if it is e raised to 0.03, then the value comes to 1.03045. So assume that the interest rate applicable for the given period is 3%. So the future value factor will be e raised to 3%, that is e raised to 0.03 for that period. When you take e raised to 0.03, the value of e raised to 0.03 will give you the final result as 1.03045. That is the factor, the future value factor. So when you take the ln of that factor, the result will be again what? 0.03. That will give you back the rate of interest. So ln of 1.03045 will give you 0.03. Let us move ahead, and under the heading continuous compounding, let us write something more. Given an HPR, that is holding period return, we can use the natural logarithm, that is ln, on your financial calculator to state its associated continuously compounded return. So RCC, R represents the return, CC represents continuously compounded, will be ln of 1 plus HPR. So keep in mind HPR is a holding period return, and when you take 1 plus holding period return, it becomes the future value factor, and ln of that factor will give you the continuously compounded rate. So I would say, notice that because the calculation is based on 1 plus HPR, we can also perform it directly from the price relative. Now what is price relative? Let me explain this to you. Before you start writing. See, imagine that you are investing $100 right now. You are investing $100, and by end of the holding period, the value is $120. So you invested $100, by end of the period the value is $120. If I assume the period to be 1 year, I would say in 1 year time $100 became $120. So what is the HPR? What is the holding period return for 1 year? In that case, holding period return without calculator, you can say 100 becoming 120, so it is 20%. So when I say 1 plus HPR, it is 1 plus 20%. 1 plus 20% means 1.2. So now pick your calculator, and what you do, 1.2, which is 1 plus HPR, you take ln of that. So 1.2 ln, that gives you 0.1823, means the continuously compounded interest rate is 18.23%. In other words, if $100 is invested for 1 year at continuous compounded rate of 18.23%, $100 of today will become $120 after 1 year. So one way to deal with this is you take 1 plus HPR. But you know, 1 plus HPR, how did we compute? We took $100 becoming 120, correct? So we computed HPR, $100 becoming 120. So it was 120 divided by 100, that became 1.2. And then we say 1 becoming 1.2. So the HPR will be 1.2 minus 1, that is 0.2, and that gives you 20%. And then again 20% you are adding back to 1. So if anyway you have to add it back to 1, why should you even bother to compute HPR? Instead what you do is you directly compute the factor, that is the period end value divided by the period beginning value. So in our example it will be $120 divided by $100, and that will give you 1.2 directly. So I want you to please understand this whole thing and carefully write the next line. The price relative is just the end of period value divided by beginning of period value. So the continuously compounded rate will be ln of 1 plus HPR, which is ln of ending value divided by beginning value. Let us take an example to understand this, that is example 30. It is exactly same kind of example that I have just explained to you. A stock was purchased for $100 and sold 1 year later for $120. Calculate the investor's annual rate of return on a continuously compounded basis. So RCC will be ln of 120 divided by 100, that will be 18.232%. If we had been given the return 20% instead, then RCC will be ln of 1.2, that is ln of 1 plus HPR, and that would also give you the same result. Well, let us move ahead and write further. A useful property of continuously compounded rates of return is they are additive for multiple periods. That is, a continuously compounded return from t equal to 0 to t equal to 2 is the sum of continuously compounded return from t equal to 0 to t equal to 1 and continuously compounded return from t equal to 1 to t equal to 2. So what exactly this paragraph is trying to convey to you? Suppose the overall investment horizon is 2 years. You find continuously compounded return for year 1, then you separately find the continuously compounded return for year 2. So year 1 standalone return, year 2 standalone return, Aggregate of that will be the overall return for the 2 years. Additive model. Now you can break this into any number of periods. For example, the investment time horizon could be 5 years. And the first 2 years, whatever be the continuous compounded rate of return that you earn, and later 3 years whatever you earn. So return from 0 to 2 plus the return from 2 to 5. When you take aggregate, it will give you the return from year 0 to 5. What I'll do is, to understand this whole thing, we will take a couple of examples to have clear understanding. But before I take you to those examples, this property you need to write down carefully. Let us move on to take up examples to understand that property. That is example number 31. Suppose we have the following stock prices for a certain asset. Price at t equal to 0, which we are calling as initial price P0, that is given as $100. Price at t equal to 1, that is 1 year later from now, P1, it is $110. And price at t equals to 2, that is 2 years later, P2 is given as $121. Calculate the continuously compounded returns for each period and verify the additivity property. Now how do we do this? Very simple. You consider that from 0 to 1, that is the first year return, $100 becoming $110, you find the continuously compounded rate of return. Then from year 1 to year 2, $110 becoming $121, you find the continuously compounded rate for the period from year 1 to year 2. Then the initial rate, that is 0 to 1, and later rate, that is 1 to 2. When you add up those two, you can verify that it will match with the rate which you can get for the entire period of 2 years, that is from 0 to 2. So let us write up that solution. So first of all, we write continuously compounded return from t equal to 0 to t equal to 2 is the sum of continuously compounded return from t equal to 0 to t equal to 1 and continuously compounded return from t equal to 1 to t equal to 2. Let us move ahead and continue further. R0 to 1, that is return from year 0 to year 1, will be ln of P1 by P0, that is ln of 110 by 100, that is ln of the factor 1.1, and that will give you 0.0953. Likewise, we take computation of R from year 1 to 2, changing the required values, we still get ln of 1.1, and that will be same value 0.0953. Now when you take the calculation of return from year 0 to 2, you will be getting ln of P2 divided by P0, that will be ln of 1.21, and when you compute that, you will be getting 0.1906. Now you check R0 to 2 will be R0 to 1 plus R1 to 2. So R0 to 2 will be aggregate of 0.0953 plus 0.0953, which will give you 0.1906. In all cases like this, you will find that this property will work 100% times. There may be fractional differences because of rounding off. You know, ultimately we are taking 4 places after decimal as rounded off value. So here in this case it matched exactly. In some cases it may not match, but the difference is not because of any other problem but the rounding off difference only. Let us take up another similar example to understand this very well. Now this is exactly similar example. What I'll do is, I'll give you time not only to note down this content, but I will ask you to do the calculations from your end. Let us check whether you have got everything correct or not. You will first compute R0 to 2, that will be ln of P2 by P0, which will be ln of 50 by 40 or ln of 1.25, that gives you 0.2231. Then R225 will be ln of P5 by P2, that will be ln of 60 by 50, that comes to ln of 1.2, and that will be 0.1823. So when you compute the return from the beginning till end, that is R0 to 5, it will be ln of P5 by P0, that is ln of 60 by 40 or ln of 1.5. When you make the calculation of ln of 1.5, it will give you 0.4055. Now precisely if you check this calculation and this calculation, you take aggregate of these two, it will give you 0.4054, but this is 0.4055. Please consider one thing, that this difference is arising only because of rounding of differences. If you convert this into percentage by multiplying each rate by 100, you will find that it will exactly match out. You can try it out definitely. So right now what I will do is to apply that additivity property. I would say R0 to 5 will be R0 to 2 plus R2 to 5, and it gives me 0.2231 plus 0.1823, which will actually aggregate to 0.4054 because of rounding of difference. So I am putting the sign over here, not exactly as equal to but similar to 0.4055. Let us move ahead and take up another example, that is example 33. If interest rate is 15% per annum compounded annually, determine the continuously compounded risk-free rate, that is CCRFI. Now understand, 15% is the annual compounded rate, means $1 will convert into 1.15 after 1 year. That means 15% should be then taken as HPR for 1 year, because 15% per annum compounded annually means for 1 year the HPR is 15%. So $1 will become 1.15. Through that you have to find CCRFI. So based on annual compounding, $1 of today will become $1.15 after 1 year. Therefore $1.15 or simply 1.15 is the future value factor. So ln of 1.15 will give you the continuously compounded risk-free interest rate, and that will be 0.1398 or 13.98%. So CCRFI, or simply the continuous compounded rate, is 13.98%. Let us move ahead and take up next example. Now here it is a little different situation. It says if continuously compounded interest rate is 15% per annum, determine effective annual rate. Now in the earlier example you have converted HPR into continuous rate. Now you are converting continuous rate into effective annual rate or a kind of HPR. So effective annual rate can be computed simply by taking the e raised to RT formula. E raised to RT, e raised to rate of interest for 1 year is 15% and time period is 1 year. Now why time period is 1 year? Because we have to compute effective annual rate, so we have to consider the time period as 1 year. But do you know what will happen? E raised to RT is not the annual rate, it is basically the factor. To arrive at the rate you need to subtract 1. So subtract 1. So effective annual rate will be e raised to 0.15 into 1. So 0.15 into 1 is 0.15. So it will be e raised to 0.15 minus 1. And when you calculate the value of e raised to 0.15, how to calculate that? You simply take 0.15 on your calculator, that is on your financial calculator. Then you have to take e raised to x function, that is you press second and then ln. It will give you result as 1.1618, but that 1.1618 is the factor, correct? So this is the factor. You subtract 1 to get the effective annual rate, and that will be 0.1618 or 16.18%.